So we were talking about dissociation constant K. I told you that if you have a weak acid, right? Whenever you have a weak acid, it ionizes but not fully. So that means that it produces an ion, an, a random ion, and releases an H plus one. So any acid does the same thing. It pretty much has the same exact equation. They always produce H plus one ions. And since they produce H plus one ions, you can think of a general equation for acid dissociation, which is this one. That you have an acid, it has H plus one, and then it releases that H plus one ion, and producing something along with that. Uh, so even diprotic acid, triprotic acid, they ionize in exactly the same way. So all weak acids, they ionize, and then we talked about how would you figure out the concentration of H plus one. So we talked about equilibrium constant, that it's I mean what you can do is just a second. I said, so what you can do over here is that to figure out the H plus one concentration, or how much H plus one is being produced, you can have take the help of Kc, which is equilibrium constant, and Kc is the ratio of the products to reactants. So if you have more products, this equilibrium constant is going to have a bigger value. If you have more reactants, that means it dissociates less, ionizes less, produces fewer ions, less products, more reactants, then it's going to have a smaller value. So we also talked about that these two ions are produced in exactly the same concentration. Like if one molecule ionizes, it produces A minus 1 and an equal amount of H plus 1. So they have the same concentration. So instead of writing A minus 1, I can substitute that with H plus 1 as well. And that would give me H plus 1 squared. Now every acid has a constant. And the higher the dissociation constant, the stronger would be the acid. Abrar, your mic is on. So every acid has a dissociation constant, and the higher the K value, the stronger would be the acid. The lower the K value, the weaker is the acid going to be. So you're going to have, and pK would be the exact opposite. Like you can express K in terms of negative of log, and those values are going to be exactly the opposite. That if you have higher K, more dissociation, more products, more H plus 1 being formed, the value of pK is going to be lower. So we did this expression, and I told you that for every acid, if you want to figure out the H plus 1 concentration, you're going to take the help of this formula. With this formula, what you can do is you can every acid has a constant. If you have the acid concentration, you can figure out the H plus 1 concentration using this expression. So we're going to do just that. For example, I have another question, and in this question, so we can start off with a few questions. So I've got a question where I have NaHSO4, and I know its concentration. That the concentration of NaHSO4 is 0.5 mole per dm cube, and I know the K value of HSO4 minus 1 ion. The K value for that is 2 times 10 power minus 5 mole squared, mole per dm cube, just mole per dm cube. And they're asking me to find the pH of this acid. Now remember, we talked about such acids that the reason you're calling this as an acid is anything that has H plus 1 or is capable of producing H plus 1. I mean, this NaHSO4 has an HSO4 minus 1 ion. So that is capable of releasing an H plus 1 ion and an SO4 minus 2 ion. So this is the dissociation that's happening for this particular weak acid. And the concentration is already given, it's 0.5 mole per dm cube. So you can you can use the K expression, which is H plus 1 concentration squared divided by the acid concentration. And if I use that, I know the K value, which is 2 times 10 power minus 5. And the H% concentration is not.
H equals squared here. I mean,
I mean, H plus 1 is squared because this is the acid dissociation equation, right? Ibrahim,
yeah.
is this clear? So
Indeed.
if I convert that into if I express the equilibrium constant for this, for acid dissociation, it's going to be H+1 concentration into SO4 minus 2 concentration, right? And that thing would be divided by HSO4 minus 1. Is this clear?
Yeah, I mean, yes.
Achha, but then I told you that this H+1 and SO4 minus 2, they would be produced in equal quantity if this dissociates.
Yeah.
So which is why these two ions are basically, they have the same value. They would be. So instead of actually writing SO4 minus 2, what you could do is you can just express it as H+1 and just square it. Is this clear?
Yes, sir. Thank you.
Achha, so the point is that your dissociation constant K is basically just H+1 squared divided by the acid concentration. So the only thing is we don't know what H+1 is. We know the acid concentration that's given over here in the first place, over here. So that is 0.5 mole per decimeter cube. So that's already provided. And what else is needed? What you need is, I mean, that's already provided. So so you can just calculate H+1 concentration. What do you get? Can anyone try and calculate this and tell me what the value is? And the whole thing would be under rooted.
(3.16 into 10 power minus 3).
So you're getting 3.16 into 10 power
minus 3.
minus 3 with the under root, right?
Yes.
As you found H+1, and if you want to find pH, you just take the negative log of this. What do we get if we take the negative log of this?
2.5.
So we're getting 2.5. That's our pH. So that is all what K is. Just remember that I mean, the only problem that people face is identifying the acid. It's I mean, some people get confused. Like we wrote we wrote many equations. So anything that produces an H+1, that's an acid. So you have to look out for these substances. Like I mean, like even in this case, the reason I gave you NaHSO4 is because the HSO4 minus 1 can act as an acid. It's capable of releasing an H+1 ion. So so just remember, H+1 squared over acid concentration is equal to Ka. And if two things are given, you can figure out the third thing. If H+1 is given, acid is given, you can find Ka. So if out of the two things are given, you can always find the third thing. So we're going to do all of this in past papers. Just remember this formula. It's H+1 concentration, and this is the formula that's going to be used for a weak acid. Is this clear to everyone, right? Adam, is this clear? Nabila, Rubab, is this clear? Mohammed, anyone? Yes or no? Is this clear?
Yes, it's clear. Yes, it's clear.
Yes, sir. Yes, sir. Yep.
Acha. Just one second. Let me. Acha, so we're going to move on. Okay, we're going to do questions later on. Later on this, when we do past papers. One second. So moving on. There's a thing called buffer solution. Now it's related to what we are just doing. So buffer solutions. Now that's this is something that's extremely important because I told you that water is very important, right? I told you that the reason we study acids and bases is that water is everywhere in your cells, in your blood, everything, all living. I mean, all everything on planet Earth is all the chemistry is it's revolving around water because water is the main solvent. So a lot depends on the concentration of H plus 1 and OH ions in the water because if it varies, then the reactions are going to get affected. Sometimes H plus 1 concentration increases, OH ion concentration, vice versa, decreases. Sometimes H plus 1 goes down and the OH ions they go up. So solutions can turn acidic, they can turn basic. Now, specifically in chemistry of life, like your chemistry or the chemistry of animals and plants, reactions are very sensitive to pH. Like every reaction in the world, it prefers a very specific pH. Because most reactions are happening inside water, so they prefer a very specific type of water.
So you can explain this hydrogen ion or hydroxide ion up and down, the concentration going up and down.
If you add an acid, what happens? An acid starts producing H plus 1 ions, right? And at the same time, the acid starts neutralizing the OH ions. So if you add an acid, the H plus 1 goes up and the OH ions simultaneously decrease. Ibrahim, is this clear?
Yes.
Okay, so that's why it's going up. If you add a base, what happens? The base, the OH ions, the base produces OH ions, right? So the OH ions, they increase, but the OH ions at the same time, they neutralize the H plus 1 as well. So the quantity of H plus 1, it goes down. Clear?
Yes, yes.
So coming back to this, reactions are very sensitive to pH. Like if your stomach is very acidic, because the reactions that are happening in your stomach, they prefer acidic conditions. But a slight change in pH can have a drastic effect on the reactions that are happening. I mean, your blood, if your blood changes pH, blood has a very specific pH. So if the pH changes, the reactions would get affected. If the soil becomes too acidic, the plants they stop growing. So everything that's around you on planet Earth that's very sensitive to pH. The pH should not change. Every reaction has a particular environment. It prefers a particular environment. So they're very sensitive to pH. So what that means is that whenever you have any solution, the pH should not change. Like your gastric juices in your stomach, the pH should not change. Because if that changes, then a lot of damage can happen. So no pH changes are invited anywhere. Like if you have a cell, if you have your blood, if you're giving water to plants, you can't give an alkaline water to it or acidic water to it. If they want a neutral water, you have to give them neutral water. Otherwise, they die. So pH should not change. So that is what a buffer is. Buffer is a solution that is going to resist a change in pH when a small amount of acid or alkali is added. Is this clear?
Yes, sir.
Yes.
So right now, I'm not going to explain what a buffer is yet. Just remember that what it doesn't let the pH change. I mean, all your biological systems, especially chemistry of life, anything that's related to, they're automatically designed to resist a change in pH. Like you can't make your blood more acidic or you can't make your blood more alkaline. Your blood is going to very, very aggressively try to resist that. It's a buffer. It's going to try and resist that. It's not going to let that happen. An example, like I'll give you the example of blood. What blood does is that the blood has carbon dioxide that gets absorbed in blood, and the carbon dioxide because of an enzyme, it changes into to hydrogen carbonate ion eventually. So your blood has a lot of HCO3 minus 1 ions. Now, if you add acid to blood, H plus 1 is added. The H plus 1's ions are gained by HCO3 minus 1 to form H2CO3. So the H plus 1 ions are removed. Now, similarly, if you add an alkali to blood, it has HCO3 minus 1, you add OH ions, right? They are added. Then all the HCO3 minus 1 ions over here, they're going to ionize. They're going to release an H plus 1. The H plus 1 is going to neutralize the OH ion. The OH ion would turn into water, and a CO3 minus 2 ion is going to be produced, which means the OH ions are neutralized. Is this clear? Is this point clear? How the blood is resisting a change in pH.
Yes.
So just because of these HCO3 minus 1 ions that are present. So it's kind of acting as an acid and a base. It's like something that's amphoteric. It's acting as an acid and a base at the same time. If you add an acid, they get neutralized because the H plus 1 get attracted to the negative ion, the excess H plus 1s, and they get removed from the solution. If you add an alkali, they start releasing H plus 1 ions, and the positive ions are going to be attracted to the negative OH ions, and they would form water, and carbonate ions are going to be produced as a result. So both H plus 1 and OH ions, they get neutralized. So your blood automatically resists a change in pH when a small amount of acid or alkali is added. Not a large amount, because if you add a very large amount, then eventually you'll run out of HCO3 minus 1 ions. And so it's only if you add a tiny amount of acid or alkali. Nothing would happen. It's going to resist it, and it won't let the H plus 1 or the OH ions increase or the numbers change. So, but how do you form a buffer in? So there are all types of buffers. So the question is, how do you form a buffer? Now, for a buffer, you need two things. Now, both those two things can be in the same substance, or they can be in two different substances. For a buffer, you need a weak acid. A weak acid is and plus its conjugate base. So that is how buffers are going to be. That is how buffers are going to be formed. That a weak acid plus its, let me just remove that. As a plus its conjugate base. These two things, they need to be mixed together. And conjugate base is usually a sodium salt of the same weak acid. I'm going to just explain this quickly. So here's an example. Like if I have a weak acid like ethanoic acid, which is CH3COOH, it would ionize, it would produce CH3COO minus 1 and H plus 1. So that's a weak acid that's dissociating. First thing, what's a weak acid? A weak acid is one that partially ionizes and produces fewer H plus 1. So the first one is that is your weak acid. So that's your weak acid, no problems over there. But remember, when a weak acid ionizes, it always produces a conjugate base. Now, a weak acid produces H plus 1 ions. A base gains H plus 1 ions. So how is this happening? A weak acid, if you look at the reaction in the forward direction, it is definitely releasing an H plus 1 ion. It is doing that. But at the same time, if you look at the reaction in the backward direction, then in the backward direction, the ethanoate ion, which is this one, it is gaining an H+1 and forming ethanoic acid back again. So which is why you call it a base. The word conjugate is used for anything that's on the right side. Like if you look at the reaction in the backward direction, you call it the conjugate reaction. Like there's a forward reaction and then there's a backward reaction. So you can call it simply a base, or you can call it a conjugate base, because it's in the reverse direction, it is acting as the base. Is this clear?
Yes.
Yes.
I mean, sir, और ये जो आपने you have written buffer equals to weak acid plus a conjugate base. I mean, buffer forms both of them.
Hamid, it's formed when there are two things present. One is the weak acid, and the other one is the conjugate base of the same weak acid. Clear? Is this clear?
So, I mean, both of them combines to form a buffer solution.
Huh. So in buffer, you need something that is capable of producing H+1 ions. And you also need something that's capable of accepting H+1 ions. You need both things. You need something to produce H+1 ions, and you need something to accept H+1. Like if H+1 goes down, I mean the concentration decreases, you need something that's capable of releasing more H+1 ions. Vice versa, if H+1 concentration increases, you need something that's capable of accepting H+1 ions. So what happens is that, for example, you have a beaker, and that beaker is a buffer. I mean the solution inside the beaker is a buffer. So it's got ethanoic acid, and at the same time it's got its conjugate base as well, ethanoate ions. So let's say from the outside I start adding H+1 ions, and I start adding, and the concentration of H+1 starts to increase. What would immediately happen is that the base would come into action. The base would start gaining those H+1 ions, and those H+1 ions are going to be removed. So the CH3CO-1 would start attracting the H+1 ions, and it would start turning into ethanoic acid, and all those H+1 ions would eventually be removed. So the buffer would try to prevent the concentration of H+1 from going up. Is this clear?
Yes.
Yes, sir.
So on the other hand, what if you start adding OH ions? So here's your solution, and you start adding, from the outside, you start adding OH ions. So the quantity of OH ions, it starts to go up. As remember, there were already H+1 and OH ions in solution, but I'm adding more OH ions. So if I start adding more OH ions, the acid would start working up. It will get activated because the H+1 in the acid would be attracted to the OH ions. So the ethanoic acid would kind of become active because the H+1 in the ethanoic acid would be attracted to the OH ions, and the OH ions will get neutralized to water molecules, and ethanoate ions would be produced because the acid has lost an H+1. So all these OH ions, they're going to get neutralized when the ethanoic acid starts releasing H+1 ions to form water back again. So it won't let the OH ion concentration increase as well. So is this part clear?
Yes.
Sir, would the acid easily give up that H ion to form water? Wouldn't oxygen hold it?
No, but now it's going to be easier. Like previously, I mean, this is what CH3 C double bond O and H is. Like this bond is very polar, right? It's positive, and this lone pairs, this is negative, right? Now, on its own, it might not ionize, right? Like the H would not be lost because the bond would be strong. But all of a sudden, when you see OH ions in the solution, OH-1, right? And let's say you added a lot of OH ions, then what would happen? The positive H will get attracted to the OH ions, and the H plus one would eventually break off. Bhaskar, is this clear?
Yes, sir.
So the point is, even at the start, if it wasn't ionizing, you adding OH ions would force it to ionize because of the
And sir, that CH3 we have, can't one hydrogen be broken off from there, from the CH3?
I mean, this one? No, not C. I mean, these bonds are very stable. These are non-polar. Like the CH,
Okay, yes.
I mean, the CH3 bonds are non-polar. They're not attracted to anything. So it's only this OH bond that's very, very polar. So that is the one that gets attracted. So just remember that all acids kind of behave in this. I mean, sorry, all buffers are going to behave in the same way. They will have, it's going to be a mixture of a weak acid and its conjugate base. And also remember that if you add a weak acid, the weak acid would ionize to produce the conjugate base, but very little amount of conjugate base would be produced in this way. So this base has to be added from outside. Because on its own, the ethanoic acid would not ionize a lot. Like if you have 1,000 molecules of ethanoic acid, the amount of ethanoate ions would produce would be very few in that case. So these ions, they need to be produced from outside. You have to add extra. You have to add extra conjugate base. Is this point clear? That on its own, ethanoic acid. On its own, ethanoic acid would not produce a lot of ethanoate ions. Like 1,000 molecules would only produce 1 or 2 molecules. You need conjugate base for this to work. So extra conjugate base has to be added, and it's usually added in the form of a salt. Like it's CH3CO minus 1. If you add that salt is going to give you this ethanoate ion. And it could be any salt, but it should be a salt that's very soluble so that it mixes easily in water, and the sodium ion, it flies off, it ionizes when you stir it in water, so you get this negative ion in solution. So that's how buffers are going to be acting. I'm going to talk about another buffer just for the sake of clarity. Let's say we create another buffer, and this time the buffer is made up of again, it needs two things. It needs a weak acid. So let's go with this weak acid, NH4 plus 1. And it also needs its conjugate base. So the solution over here is going to have a lot of NH4 plus 1 ions, but you also need a lot of conjugate base as well. So what would happen if you try to make this acidic? You start adding H plus 1 ions. So all of a sudden you started adding H plus 1 in the solution. The buffer is not going to let that happen. The lone pairs on NH3, I hope you remember they were lone pairs on NH3. They would start to gain H plus 1 ions. And they would start forming NH4 plus 1. So the H plus 1 ions are going to get neutralized because they would be accepted by the lone pairs on NH3 or get attracted to the lone pairs on NH3. Is this clear? Is this clear or not?
I mean, the hydrogen that is produced is it an ion or is it an atom?
Sorry, that's an ion. Okay, we're talking about this buffer, that this is behaving as a buffer. Okay, if you have in your solution a lot of NH4 plus 1 ions and you have a lot of NH3 ions, so not ions, NH3 molecules, then it would act as a buffer. And similarly, if you add OH ions, and if you start adding a lot of OH ions to solution, they're going to get neutralized as well. Because if you add a lot of OH ions, the H plus 1 from NH4 is going to be attracted to the OH ions, and they're going to form water, H plus 1 and OH ions, and NH3 would be left behind. So basically the reaction over here, the equilibrium over here would shift forward or backward depending on what's happening to H plus 1. Like if H plus 1 goes down, its concentration decreases. That means more forward reaction would happen. If H plus 1, like this one, which one is the forward reaction? If H plus 1 goes down, there's going to be more forward reaction, and NH4 plus 1 would get converted to NH3. So that's what's happening. If H+1 concentration goes up, then the reverse reaction would be happening. Is this clear?
Yes, sir.
Yes, sir.
So now, just 1 second. So now this one next thing is that so just remember what you're going to mix to form a buffer, and every time it's basically the same equation. I mean, even in the buffer, it's the same acid dissociation equation. Like the same equation where HX releases an H+1 and it's in equilibrium. It's the same equilibrium reaction that's happening. It's either moving forward or backward depending on the concentration of H+1. The same thing pretty much happens over here as well. Like this whole thing that's happening, it is the same equilibrium that's moving forward or backward. Like the CH3CO -1 ionizing. And it's moving either forward, like if H+1 decreases, it's going to move forward. The ethanoic acid would turn into ethanoic, so the ethanoic acid would turn into ethanoic if H+1 decreases. Vice versa, if H+1 increases, it's going to move backwards. And in that case, the reverse reaction would happen. The ethanoic would gain H+1 to form ethanoic acid. So it's the same acid dissociation equation, no different. It's exactly the same. In the buffer solution, the same reaction is happening. It's just moving backward and forward depending on what you're doing to the concentration of H+1. Is this clear?
Yes,
Yes,
sir.
sir.
Yes, sir.
So that means that you have the same K. I mean, I'm going to write it. You're going to have the same K. It's the same equation. So it's going to be K would be like it's the same acid dissociation equation moving, not A -1, X -1, moving forward and backward. But remember the K is always a constant, even if it only changes with temperature. So it's going to be the product concentration into H+1 concentration divided by the and the other way to write this equation is this is your conjugate base and that's your acid, weak acid. So the other way to write this thing is that it's basically conjugate base concentration into H+1 concentration divided by the acid concentration. And the other thing is you can't make it H+1 squared now. Why? Because these two ions are going to have different concentrations. You added this ion, you added extra ions of the conjugate base. You added more of the conjugate base from outside. Is that clear?
Yes, sir.
Yes, sir.
Okay, now these two ions are going to have different concentrations because this has been added from outside. Mohammed, is this clear? Ethan? Minail, is this clear?
Yeah.
So here, let's continue with this tomorrow then, okay?
Chalo, okay, sir. Thank you.
La-
Right, sir. Love this, sir.
Okay, take care, Allah Hafiz.
Thank you.